Hello everybody, welcome to today's lecture on material balance calculations for multiple unit processes without reactions. In most cases, industrial processes are not single unit processes. There are multiple units which are connected together to perform an overall process. This type of a system is represented using a process flow sheet or a flow chart, which is basically a graphical representation of the process. This provides sufficient detail to formulate material and energy balances, and it can also be used for troubleshooting and for controlling the operating conditions and optimizing the conditions. Instead of drawing a process flow sheet, which is quite tedious, we can also draw something called a block diagram, which is basically representation of the process using blocks or squares. So this is a flow chart. What you see here is feed entering, getting mixed with a low pressure recycle, then getting pumped to enter into a heat exchanger, then again getting pumped to be mixed with a high pressure recycle, and the mixture entering into a reactor, and the product of the reactor comes and is cooled by two different heat exchangers. The exit of the heat exchanger enters into a high pressure flash, and the products of this high pressure flash either gets recycled or purged, and the recycle stream is pumped to form the high pressure recycle. The other product stream of the high pressure flash is then sent to a low pressure flash, where ammonia is recovered and the low pressure recycle is sent back to be mixed with the feed. So this process flow sheet gives you all the details of the process which is happening. As you can see, individual processes are represented using proper diagrams which represent what type of a system it is. For example, a pump is represented the way it is shown here, and you have the heat exchanger which is shown here, and you have the reactor which is shown here, and again heat exchangers and high pressure flash, low pressure flash, and so on. In case this is too tedious, you can also draw something called a block diagram which is shown here. So the process which we just described earlier is exactly depicted in this block diagram also. However, instead of using specific representations for individual processes, here we just draw blocks with proper labels. So these are two ways to represent a multi-unit process. So let us look at a multi-unit process as an example. So here is an example problem where you have two feeds which are getting mixed to then enter into a unit 1. A product stream is recovered from this unit 1, and another product stream which leaves unit 1 is split into product 2 and the input for unit 2, and this unit 2 has another input which is feed 3, finally forming product 3. So this particular process can actually have multiple systems. The way we defined a system earlier was any portion of a process that can be enclosed by a hypothetical box. This means we can actually draw different boxes to represent what each of these systems would be. This is the overall system. You see that every process which happens within the system, every single unit which is present within the process has actually been encompassed by this overall system. This makes sure that there is only feeds which are crossing the system boundary and products which are leaving the system boundary. It does not account for the mixing points or the splitters or the units separately. So this is called the overall system. Instead of drawing something like this, you can also draw boxes which cover the individual systems. For example, you could have only this mixing point as the system, or only unit 1 as a system, or the splitter as a system, or unit 2 as a system. In addition to this, you can also draw combinations of these as systems. You could have B plus C as a system, or C plus D as a system, or you can have B plus C plus D as a system, and so on. So drawing this system makes sure that you actually have a portion of the process which you are going to be observing. So you will perform the material balances using this as the system and considering the streams which cross the boundaries of this system as your inputs and outputs. This means there are actually multiple systems which we can study. In a single unit process, we had only one system and it was simple to study. So here, because there are multiple systems, where do we start? The most accurate way is to perform degree of freedom analysis for each of the subsystem which we drew and start from the subsystem which has 0 degrees of freedom. This process is very time consuming. So instead, a simple and more efficient way would be to start with the overall process as a single system and then continue with individual processes to perform the overall balances. So when we consider this overall process as the single system, then what happens is the entire process becomes like a single unit system, and the the material balances performed will be similar to what we have done earlier. Another approach would be to start with either the final system or the initial system. So, how do we approach these problems? First, we write the overall balances for the systems which are containing all the units, which is the overall system, and then we can write the balances on for each of the systems which makes up the overall system, and we can also make combinations of 2 or more subunits to form a system and thereby write balances for these. We need to be careful and write only independent balances. Generally, one independence balance can be written per component for most of the systems except for splitters. As we already saw, splitters have only one independent mass balance equation, which is the total balance equation. Now, having looked at this, we will see 3 different example problems, each of them using different approaches, which helps us in identifying how to solve these multi-unit processes. The first example is given here. A labeled flow chart of a continuous steady state 2-unit process is shown below. Each stream contains 2 components A and B in different proportions. 3 streams whose flow rates and or compositions are not known are labeled as 1, 2 and 3. Calculate the unknown flow rates and the compositions of streams 1, 2 and 3. Now, this process has one input which enters into a particular process giving 2 outputs, and one of the output leaves as a product and the other one gets mixed with another input. So, this mixed input enters into the second unit forming 2 different product streams. So, this is what the system represents, this is what the process represents. Now, what are the systems which we can draw for this process? Just like how we saw in the previous illustration, we can actually draw the overall system which contains all the units which are present. So, which is the unit 1, your mixing point and unit 2, all of these together forms an overall system, or you could consider only the unit 1, only the mixing point and only the unit 2. You could also have combinations of unit 1 and mixing point or mixing point and unit 2 and so on. So, now that we have the possible systems, we will start with the overall system. That would be the easiest and efficient way to solve such a problem. Okay, let us now start solving this problem. We have multiple systems that we have chosen and we need to identify which system to start our calculations with. Before we do that, let us identify what the basis for this system would be. So, for this process, we will have to use the basis as given flow rates, as we have multiple flow rates that have been provided. Once we choose the basis, we now have to identify which system we want to start with. So, we have multiple options. We will first start with the overall system. Why do we want to start with the overall system? If you look at the different systems, the overall system actually gives you one information, which is the unknown is only one stream, which is M3. You do not know information about the product stream, which is the mass and the composition of the product 3 stream. All the other streams which are crossing the system boundary are unknown. So, we could start with the overall system. Let us start with this and perform these calculations. For the overall system, we can write a total balance as input minus output plus generation minus consumption equals accumulation. Assuming steady state, accumulation goes to 0, and as the system does not have any reactive processes, generation and consumption go to 0, giving you input equals output. The input streams are one stream which is entering at 100 kilograms per hour and the other stream which is entering at 30 kilograms per hour. So, input is 100 plus 30 equals output streams which are 40 plus 30 plus 40 plus 30 plus M3. So, now using this equation we can calculate M3 dot as 60 kilograms per hour. So, now that we have calculated the mass flow rate of the product stream 3, we need to calculate the composition of product stream 3. That we can do by performing component balances for this stream. We will first write the component A balance. So, what we have is 2 input streams where the compositions are known. So, it is 0.5 times 100, which is A entering through this stream, and it is 0.3 times 30 based on A entering through the other stream, and you again have output streams which are 40 times 0.9 plus 30 times 0.6 plus M3 dot times X3, where X3 is the composition of A in the product stream 3. So, why we have written this is we have again assumed input equals output because generation and consumption are 0 and the process is at steady state. So, from this we can calculate X3 as 0.0833 kilograms of A per kilogram. So, from this we have the information about the product stream 3. So, the product stream 3 basically contains 60 kilograms per hour product 3, which contains 0.0833 kilograms of A per kilogram. So, and the rest, which is 0.9167 kilograms, would be the composition of B per kilogram of the product. So, this gives you the information about product 3. So, the next step is to calculate the information for the streams 1 and 2. So, let us start with unit 1, let us just call this as unit 1. So, when we write a balance equation for unit 1, we will be able to get information about the stream 1. We can write a balance equation for unit 2 to get the information for stream 2. So, let us first start with unit 1. With unit 1, we have a total balance equation which will come down to input equals output, which is 100 equals 40 plus M1 dot. So, this gives you M1 dot as 60 kilograms per hour. Again, by writing a component balance for A for across unit 1, we can write it as input equals output, which is 0.5 times 100 equals 0.9 times 40 plus x1 times M1 dot. As we already know M1 dot, we can calculate x1 as 0.233 kilograms of A per kilogram. So, the product stream which is leaving the unit 1, which is the stream 1, basically contains 60 kilograms per hour with 0.233 kilograms of A per kilogram and 0.767 kilograms of B per kilogram. The composition of B is basically 1 minus the mass fraction of A. Now, we need to calculate the information for product stream 2. So, for that we could either write a balance equation for unit 2 or we could write a balance equation for the mixing point. Either of this would give us the information about product stream 2. Now, here I have chosen to write the balance equation for the mixing point. Using the mixing point, we have M1 dot plus 30 kilograms equals M2 dot as the total balance. So, this is the total balance. From here we already know M1 dot. So, we can calculate M2 dot as 90 kilograms per hour. We can again write a component balance for A across the mixing point as x1 M1 dot plus 0.3 times 30 equals x2 M2 dot. Solving this equation, we can get x2 as 0.255 kilograms of A per kilogram of the mixture. So, this means the stream 2 basically is 90 kilograms per hour containing 0.255 kilograms of A per kilogram and the rest, which is 0.745 kilograms of B per kilogram. So, these three things which we have now calculated gives us the information about the mass flow rates of the streams 1, 2 and 3 and their compositions. So, with that we have solved a multi-unit process. What you understand here is we used an overall system which basically made the multiple units into a single unit process, and then we broke down individual units and started solving the material balances for each of them separately. With this we were able to get all the information that was required. In the next lecture we will look at more example problems. So, we will look at an example problem where we approach a multiple unit system with a different approach rather than starting off with the overall system. Thank you.